Hello, and welcome to your Advanced Statistical Inference Part 2 lecture. So we spent the last lecture talking a little bit about how to actually do a Bayesian regression, and now I want to talk a little bit about what you might do once you've fitted and analyzed that regression. The first and main thing we're going to talk about today are predictive checks. Predictive checks use predictive distributions to basically say what is the likelihood of observing various data given the fitted model. For instance, one thing that you may have done in previous courses where you learned regression models is you use that regression model to actually forecast or make a prediction for a data point that you don't know the actual answer for. But how do we make predictions with a Bayesian model where we don't have a single estimate of our parameters? Rather, we have distributions that quantify the uncertainty we have about the actual parameter values. And this can apply to any distribution of our parameter values. For instance, we could look at our posterior, which is what we think about parameter values after seeing the data, or our priors, which is what we think about the parameter values before we see our data. So predictive distributions, both prior and posterior, account for two different sources of variability when making these predictions. First, they account for distributional variability. This is representative of the uncertainty we have about our parameters. Yes, we might have a mean estimate for the parameter or a median estimate for the parameter, but remember, the whole point of Bayesian statistics is that we're quantifying our uncertainty about parameter values using distributions. And so, of course, when we make predictions, we don't want to reduce that rich source of information down into a single point estimate. And so how do we take into account that uncertainty that we have about what the parameter value is? The second source of variability that we take into account is sampling or data variability. This has to do with the inherent variability of data. Even if we knew the exact perfect regression model that predicted the relationship between our inputs and our output, there's still going to be variability of the data around that regression line. This is what sampling variability accounts for. So what does this look like? Well, for distributional variability, this just looks like our distribution of parameter values, either the prior distribution or the posterior distribution. The more certain we are about what the parameters are, the lower the variability that we'll have in terms of distributional variability. The more uncertain we are about what the parameter value is, the higher the variability we'll have for distributional variability. In other words, distributional variability allows us to quantify how certain we are about the value of the parameters of our model. If we're really uncertain about what the coefficients and the intercept of our model is, we should also reflect that when we're making predictions about future values. For instance, let's say we're looking at a regression at the relationship between corgi height and corgi weight. If we're really unsure what the coefficient between corgi height and corgi weight is, then that should be reflected when we predict future corgi weights. One thing I want to point out here is that this is the type of variability that we have the most control over, either through priors or by increasing the signal in the data, so increasing sample size or getting lower variance samples. We can actually improve our estimates of what parameters are. So while it might not be the easiest thing in the world to increase your sample size or choose more informative priors, we do have a lot more control over what this variability is. On the other hand, sampling variability is not something that we're able to control. It's the inherent randomness of data around its expected value. In other words, sampling variability answers the question, how much will the observed data typically vary from its expected value? And this is just sort of an inherent property of the data given the different variables you're using to predict. No matter how much we increase our sample size, even if we had the exact perfect regression line that perfectly described the relationship between our inputs and our outputs, sampling variability would remain constant because it's this inherent randomness of data around their expected value. And even if you have the exact correct model, that variability will still be there. But it is still important to include this variability when we're making predictions. not only do we have uncertainty about what the actual model parameters are, but also even if we knew the exact correct parameters, there would be some variability of the samples around that expected value that we want to account for. Predictive distributions basically say, what is the probability of certain values given the data that we've already observed? The way we actually calculate predictive distributions in practice is we first draw a set of parameters from our distribution, either our prior or our posterior. So if we were fitting a regression model, we would pull a random sample of our parameters, so maybe the variance of the model, the intercept, and the coefficient. And then we would use, in step 2, those parameter values to then generate data. So again, there's 2 steps to actually get the predictive distribution. First, we're going to randomly sample a set of parameters from our prior or our posterior, and then we're going to use those parameters in a model and use that to generate a new sample of data. The first step accounts for uncertainty we have in the parameters. Because we're going to repeat this process over and over to get a bunch of samples, we are going to inherently reflect the uncertainty we have about the parameters because each draw of the parameters is going to be slightly different. The more precise our estimates of the parameters, the less these thetas that we draw are going to vary, which is going to reduce the variability in our predictive distribution. But still, whether it's huge or very small, step 1 allows us to reflect that variability due to the uncertainty we have about our parameters. Step 2, on the other hand, allows us to account for that sampling variability. Even if we had the perfect model, what is the variability of data around its expected value according to the model? Now, if you notice that your predictive distribution is far too wide to be useful, again, it's usually easier to control the distribution of parameter values by setting more regularizing or informative priors or grabbing more data so that you have more information coming in through the likelihood than it is to reduce the actual sampling variability. So if you're ever in that situation, you should really look to step 1, the distributional variability, in order to reduce that overall predictive variability. So again, predictive distributions have 2 sources of variability that they account for. First, they have distributional variability, which is our uncertainty about the parameters of our model, and 2, the sampling variability. How do data points vary around their expected value from the model? So how can we use these predictive distributions as a part of our Bayesian workflow? Well, the first part is something called a prior predictive check. As the name implies, a prior predictive check allows you to simulate samples from your prior and make sure that those simulated samples of data line up with your expectations about reality. We can then compare this both to our expectations as well as to our actual data. Remember, our goal when building a model, Bayesian or not, is to create something that describes the world well. And so if our prior distribution allows us to generate samples of simulated data that make absolutely no sense, it's probably a sign that our priors themselves make absolutely no sense and that they should be modified in some way. Here's how you would run a prior predictive check in the BRMS package. First, we would have to, of course, set our priors for the model and then fit a regression model. Here, we're fitting a very simple regression with only one predictor X and one outcome Y. We then use this argument sample prior equals only to tell the model to only sample from the prior and not use the likelihood to update the prior to give us the posterior. Once we fit that model using only the prior, we can feed that fitted model into the unfortunately named ppcheck function, which allows us to do this prior predictive check. You can get a lot of different graphs from this function, but the default is something that looks like this, which shows the density both of your original data shown in kind of solid black and with a bunch of different samples pulled from that prior shown in this lighter transparent blue. What we're looking for is twofold. First, we want to make sure that the priors that we use are relatively reflective of our data. We don't want the data that we've seen to be completely impossible based on the priors that we've chosen. And just from this graph alone, we can see that that's pretty true. Our observed data is well within the normal values that we're seeing of samples that are pulled from our prior. The second thing that we want to look for is we want to use our subject matter expertise to make sure that the simulated values we're getting make sense. For instance, here you can see that at least in some of the draws that we got from our prior distribution, we're getting really extremely negative values, about -20. And in other draws, we're getting extremely positive values, like all the way up to maybe 25. Using our expertise about the data that we're fitting, we also want to use this prior predictive check to understand whether that's realistic. Let's say that, as usual, we're looking at a survey of depression and that most people have scores between, say, -5 and +5. Knowing that about the context of our data might cause us to say, oh, there's something off about our priors because we're getting really extreme depression scores, both on the negative side and the positive side, that as subject matter experts, we really wouldn't expect to see. And so maybe we need to narrow in our priors so that the data simulated from them is a bit more realistic. So given that we're seeing these really extreme values, let's make some adjustments to our priors so that hopefully they simulate more realistic data. Basically, it looks like we're giving our intercept and our coefficient slightly too much leeway to be really extreme values, and this is generating data that's far more extreme than we would ever expect to see. All right, so now we're adjusting our priors to be a little more realistic. I've reined in the priors, especially of the intercept and of the coefficient, to be slightly narrower and more informative that will hopefully generate values that I think are more reasonable. And here you can see that's exactly what happened. When we did a new prior predictive check, you can see that our data is definitely well estimated by the samples from the prior. However, it's also giving much more realistic values. Remember I said we can assume maybe that depression scores are, for most people, typically between -5 and +5. Well, if that's the case, then pretty much all of the draws from our prior are giving us values that are reasonable according to that metric. And we don't just have to stick to priors. We can also do posterior predictive checks, which unfortunately also are abbreviated PP check. Posterior predictive checks are the exact same thing, but the distribution we're using to draw our parameter values from is the posterior, our beliefs about the parameters after seeing the data. Similar to the prior predictive check, the goal of the posterior predictive check is similar. It simulates new samples of data according to our posterior. Now, like with the prior, this allows us to basically look for any systematic discrepancies between the real data that we've observed and the simulated data. This is a quote from Andrew Gelman, one of the huge names in Bayesian statistics, and he basically goes on to say that this can help tell us a little bit more about whether the model that we've generated is a good fit. If our posterior is generating samples that are super different from the data we've observed, then maybe our model's not a great fit to the data that we've observed. Similarly, if we're seeing generated values that are completely beyond what's reasonable or possible according to our subject matter expertise, we can also pick that up with a posterior predictive check. Luckily, the way to run a posterior predictive check is exactly the same as a prior predictive check. The only difference is we can use our actual fitted model without saying the sample prior equals only. So essentially we're saying, hey, actually do the posterior calculation, and then when we do our predictive check, use the posterior, not just the prior. Unfortunately, the image is a little small, but if you pull up your slides, hopefully you'll be able to see that in our posterior predictive check, our data is very typical according to the samples drawn from the posterior. So this gives us at least a little bit of evidence that our model is a good fit for the data that we have. And believe it or not, Bayesians also use p-values, but not quite in the same way that frequentists do. Remember that p-values, just in general, tell you, given a specific distribution, what is the probability of observing an estimate as or more extreme than the one that we did. In other words, it tells you a little bit about how consistent our data's estimate is with the distribution that we're assuming. Now, in frequentist statistics, we use this for null hypothesis significance testing. We assumed a null distribution and saw how extreme or how compatible our test statistic was with the null distribution, but now we have a new way to apply p-values. Here, p-values play a role in our posterior predictive checks. For instance, we can eyeball a bunch of graphs like we have been doing on the last few slides that tell us how consistent the samples from our prior or our posterior predictive distributions are with the actual data we observed and with our expertise. But we can also, especially if there's a really complicated model, use p-values to do something similar. In essence, what we do is we generate a bunch of samples from our predictive distribution, and then we look at what proportion of those values are as or more extreme than the ones that we saw in our actual data. For instance, here, maybe the statistic I want to look at is the mean of my sample. First, I would use the fitted model to draw 500 samples from, in this case, my posterior predictive distribution. Then I define the function that I want to use to calculate my statistic. In this case, it's really easy. It's just the mean. Then I can calculate the observed mean. So this is the mean for the sample of data I actually have. And lastly, I can calculate the same function for all of my posterior predictive samples. In this case, we have 500 samples. So I just take the mean of all of those samples that we generated from the posterior predictive distribution. Then all I would have to do is either graph or calculate an actual p-value. In this graph, what you can see is a histogram showing the mean value of each of my 500 posterior predictive samples. And the line, the dark blue line you can see in the middle, is showing what the actual mean for my observed sample is. Now, this p-value would be pretty high. Most of our samples are as or more extreme than the actual data that we observe. So our data is pretty consistent with the posterior distribution. Now, what might be a problem is if we saw that our observed statistic, say the sample mean, was incredibly different and far more extreme than the means generated by the posterior. This would indicate that there might be some mismatch between our posterior and the actual data. And remember, we want to make sure that our model is reflective of the real world. And all we know about the real world at this point is what we learned from the data. So we want to make sure that the models we're creating are actually in line with that data. All right, so let's walk through a Bayesian regression workflow in R. To start off, we're going to start simple. We are going to use the MT-CARS data that's available just in R alone. The first thing we, of course, need to do is actually look at our data. Here you can see we have a ton of data based on the performance of cars. So, for instance, we have the miles per gallon the car gets, horsepower, all of that good stuff. We are going to use some of these variables to predict MPG using a linear regression model. Now, the first thing that I want to do is set up my actual regression model. Here I have my regression model that's predicting miles per gallon based on horsepower and number of gears. Using the BRM package, I can just specify this like I would a frequentist model in R. Now, one of the things you might have noticed is that I didn't set any priors like we have in examples previously. And that's because in the BRMS package, there are things called default priors. Now, I don't always recommend them, but they can be a good place to start if you're not sure what types of priors you should put on your various coefficients. Now, in order to see what priors that a model is using, whether you specified it or you're using the defaults in the BRMS package, you can use the getPrior function, which will allow you to see a readout of all of the priors. Now, notice for coefficients in the model, specifically for our gear and HP coefficients, we have no informative prior. We basically have a flat, uninformative, uniform prior over all possible values of the coefficient. So we are implicitly assuming that any possible value in the real numbers for a coefficient is equally likely. Now, this might not be a reasonable assumption, so we may want to come back to that, but at least this is telling us what that default prior is. Interestingly, BRMS has pretty good weakly informative priors for the intercept and for the variance of the model. You can see that we're using student t distributions with various parameters, but this is basically to show you that no matter how you set your priors, whether you let BRMS set them for you, not always a great idea, or you set them yourself, you can always check what priors are being used with this getPrior function. Now, I don't think those priors were particularly reasonable, especially for the coefficients. I just do not think a flat prior is reasonable in nearly any case. So I'm going to set a very weakly informative prior. I'm going to use a normal distribution with a mean of 0, so I'm not assuming that the effect is positive or negative. It's pretty much equally likely to be either. And a standard deviation of 5. This is a very wide prior. A lot of different coefficient values are possible, but it's at least weakly regularizing, meaning that very, very extreme values, which we know are impossible, are not given much weight in the prior. Here again, you can see, even though I set some of these priors by hand, you can get a full readout of what the priors are using get prior. Notice that when I set this prior, I set class equal to B. This basically says for all of the regression coefficients, so anything that is in the family of a regression coefficient is going to use this same normal 0.5 prior, and you can see that's in fact what has happened here. Now that I have a reasonable prior, maybe I want to do a prior predictive check. So I fit my model using sample prior equals only, and I feed that fitted model into the ppcheck function. Now, one thing I notice here is that while my data doesn't completely fall outside of what's reasonable with the prior, my data is far narrower than the values of the prior imply. So maybe if I had a little bit more time, I would go back and choose more informative priors that are reflective of what I actually expect to see. Here we're seeing predicted miles per gallon that are much, much higher than we would ever expect to see in real life. I'll leave it as an exercise for the viewer to go back and copy this code and see if you can come up with priors that might be a little more reasonable given the scenario that we have, which hopefully you know a little bit about cars and miles per gallon, so you could figure out what are some reasonable values for coefficients here. But let's go with our very wide priors and look at the summary of a fitted model. So here we fit a new model using the same syntax as before, but instead of saying sample prior equals only, we just remove that argument altogether. So we actually get our fitted model using the posterior. And then we're looking at the summary of this model. Now, probably the most important thing to look at the beginning is to look at the estimates of our coefficients. These are going to be the typical or the best guess for each of our parameter values. But remember, we're in a Bayesian framework, so we don't just want point estimates. We want to reflect the uncertainty that we have about these parameter estimates. And that's exactly what the rest of the output will give you. So here we have our estimate error. This is basically the standard error of our estimate, and this is used to help calculate the 95% credible interval. You can use a different percent if you want, like 90 or 50%. By default, it'll give you 95%. For instance, here we could say that there's a 95% chance that our intercept value falls between 11.34 and 24.61. If we were, for instance, looking to test whether the intercept was different from 0, this would be a resounding yes. 0 is not even close to our 95% credible interval, so we could pretty much say 0 is not a reasonable value for the intercept. However, typically we're not usually interested in the intercept, we're more interested in the coefficients of our model. And in both cases, we have pretty precise estimates of what we think those coefficients should be. For horsepower, we have a negative 0.06 coefficient. So as horsepower increases, we actually expect MPG to decrease. And this kind of makes sense because the more horsepower, like the more powerful your car is, it's probably going to be less fuel efficient. And you can see from our 95% credible interval that we're fairly certain that this coefficient is negative. We do not think it is reasonable that increasing your horsepower would increase your miles per gallon. And the opposite is true for gear. Depending on the number of gears, we think there is a positive relationship. The more gears, the more miles per gallon you get. And looking at the credible interval, we're fairly certain that this is positive as well. There's a 95% chance that the coefficient for gear is between 1.63 and 4.66. Now notice that this regression output also gives you some convergence metrics. For instance, we have R hat as well as our effective sample size. Remember, for R hat, we want this value to be as close to 1 as possible. And luckily, all of our R hats are 1, indicating that when we're sampling, it's likely that we reached convergence because the within-chain variability and the between-chain variability are roughly the same. We also see really high effective sample sizes. Typically, we want about 100 times the number of chains. Default number of Markov chains would be 4, and this is well above that. So we also have pretty efficient sampling. Now, R-hat is a really great overall metric, but often we also want to look at the actual trace plots for our different parameters to make sure they're very fuzzy caterpillar-like. I had to zoom in a lot so you could actually see what was going on, but here you can see that the MCMC trace function, given a fitted model, will allow you to see the trace plots for all of the different parameters in the model. For instance, here we can see the trace plot for our two model coefficients for HP and gear, and you can see indeed they look very fuzzy caterpillar-like, meaning that we have reached convergence in our MCMC chains. Now that we've actually fit the model, we can do a posterior predictive check, and luckily this graph is much larger, so you can see that our actual observed data shown in the black kind of bold line is pretty consistent with the samples that we've drawn from our posterior. This is a good sign and indicates that we probably have a pretty good model fit here. It's not foolproof, but it's good evidence that nothing really wonky is going on. And now that we have our fitted model, we might want to focus in more specifically on whatever it is that we're interested in. For instance, let's say we're interested in parameter estimation for the two coefficients in our regression model. I can use the MCMC areas function, give it my fitted model, and allow it to plot just the parameters for my coefficients for horsepower and gear, and it will give me out this density plot of the posteriors for each of those values. Because this is just a ggplot that MCMC areas outputs, I can also add on top of it geom-v lines indicating our region of practical equivalence. Let's say that because of my vast expertise, I happen to know that any coefficient between negative 0.1 and positive 0.1 is practically 0 when it comes to miles per gallon, so I've added that to our graph. This allows us to visualize the uncertainty that come with our posterior estimates of these coefficients, and even do things like visual inspection of a rope. For instance, we can see that based on our definitions here, for the coefficient of gear, it is far outside the rope. Pretty much all of the posterior distribution is outside of the rope, whereas for horsepower, it's almost entirely within the rope. Now, something you might want to think about here that I want you to think about more critically on your own is whether we can use the same rope when it comes to gear, which only has a couple of different options, versus for horsepower, which has a lot of different options. It has very wide variability. If you want to read more on using rope with the BRMS model, go ahead and click this link and you can read a little bit more about how you can actually implement it. But visually, MCMC areas is a great first step for plotting your actual posterior distributions so that you can look not just at point estimates and interval estimates, but at the entire density of the posterior distribution. Last but not least, I have two examples that I'm briefly going to go over, but I want you to look at a little bit more closely on your own. Here we have a logistic regression that's looking at whether or not students passed a standardized exam based on their parental income. Here in this R code, all we're doing is loading in the necessary libraries that we'll need for this analysis and simulating our actual data. Of course, normally what you would do is you would read in data that you're actually interested in working with, but for the sake of teaching, we're going to simulate the data so that we know exactly what the data should say. So now that I've read in that data, I can look at it, DF, and we can see it has in it the income of parents in thousands, as well as whether or not their kids passed the exam. So as you can maybe guess, we are interested in whether parental income is affecting whether or not kids passed an exam. So the first thing I'm going to do is I'm going to fit a model. I'm going to specify some pretty wide priors, and then I'm going to fit a model using the BRM function from the BRMS package. Just like with a frequentist model, I can specify what I want to predict on the left-hand side of the tilde and all of the predictors I want on the right-hand side. Then I'm going to provide it with the data and all of these different arguments that help us fit our model. Family, as we discussed before when we talked about generalized linear models, tells us a little bit about the likelihood for the data. Because we're fitting a logistic regression predicting a binary passed or not passed, we're going to use a Bernoulli likelihood. And then we're going to feed in the model the priors, the list of priors that we defined above that we want to set for all of the different parameters in our model. For anything that we do not set a parameter for, the model will use its default prior. These last four arguments are more about how the model is fit than the actual structure of the model, but they can be pretty important. Seed, as you can guess, gives a random seed to the function so that your results are reproducible, especially given all of the randomness inherent with MCMC sampling. Chain says how many Markov chains do you want in your MCMC algorithm. Default is 4. I think that's a pretty safe space to start. It's not too computationally expensive, but does give you enough evidence that the starting point of your Markov chain isn't going to affect where it converges to. Cores tells your computer to assign different chains to a certain number of cores that you may have available on your computer. And iter tells us how many iterations or how many steps in our Markov chain are we going to have. For example, let's say your R hat is bad or your effective sample size is low. One possibility, though it's not guaranteed, is that your chains just have not converged yet, and they might need more iterations in order to get into that steady state where they're sampling from the actual posterior distribution. If you ever run into things like that, making sure iter is a little bit higher is a great idea. Now remember, this will make it take longer for your model to sample, but it gives the chains more time to get to that target distribution. All right, so I'm gonna go ahead and run this, but I'm gonna cut out the running because it does take a few minutes to fit, and we'll come back and we'll look at the summary of the model together. All right, so my model is fit. Let's look at our summary. You can see here exactly what we looked at together in our slides. You can see that we get our regression output, and what we're probably most interested in this case is the coefficient of parental income. This basically tells us that as parental income increases, the log odds of their child passing the test also increases. But if you look at our 95% credible interval, we're not positive that it's going to be a positive coefficient. There is some negative values in the lower end of our credible interval. So we couldn't definitely say that 0 is an unreasonable value. So it's possible that parental income has no effect on whether or not the kid has passed the exam. However, most of the posterior is above 0, so there's a pretty high chance that there is some positive effect of parental income on whether the kid passed their test. Just like before, we can also look at our convergence metrics, and I don't see any red flags here. It doesn't mean that everything's perfect, but our R hat is exactly 1, meaning that the within chain and between chain variance is very similar, and the effective sample size is high, meaning our samples are hopefully pretty efficient. Just to double check, we can also look at trace plots. If I use MCMC trace on the model, it will give me a trace plot for every single parameter. And you can see that all of them pretty much look like fuzzy caterpillars, so more evidence for convergence on our side. I might also want to do a posterior predictive check by running ppcheck, and you can see that our data is very consistent with samples drawn from the posterior, so I don't see any red flags here either. It looks like our model is a pretty good fit. Last but not least, I may want to present the results to someone. So I'm also going to look at the actual full posterior of my parental income coefficient. Here you can see basically what we saw from the regression output as well, where you can see here our 50% credible interval shown in light blue, as well as the entire posterior distribution shown in the density. Like I said before, 0 is not an unreasonable value according to this posterior, but a bulk of the posterior density is above 0. So I would not be certain, but I would be fairly confident that there's a positive effect of parental income. My best guess would be around the mean of the posterior. I might here report what the 95th percent and the 50th percent credible interval is to help communicate uncertainty we have around what this coefficient is. Now, we can do something similar, but we'll use a mixed effect model using the BRMS package. We are again going to load in the necessary libraries and simulate our data. Here, similarly before, we're looking at the influence of parental income, but this time instead of on pass rates, we're looking at actual exam scores. So we're going to go ahead and simulate the data, and then we're going to build our model. So again, our goal here is to see, does parental income influence the exam scores of their children? Like before, the first thing we probably need to do is set up priors. I'm going to set pretty diffuse or like weakly informative priors. For my coefficients, I'm going to say mean of 0, standard deviation of 10, which allows for a really wide range of both positive and negative coefficients when it comes to parental income. And I am also going to put a pretty weak prior on the intercept. This says that I think the intercept, so basically if parental income was 0, what is my predicted exam score, is going to be around 50 with a standard deviation of 10. So there's a lot of uncertainty around that value. Then I'm going to go ahead and fit my model. Just like we've talked about before when we talked about mixed effect models, we are going to set up the formula for our regression as the thing we're predicting tilde all of our predictors. Note, we use this pipe structure to indicate random effects. Here we're saying both intercept, represented with a 1, and parental income are going to have different values based on the school that we're in. Essentially, we have random intercepts and random slopes for school. This means that schools can have different intercepts when it comes to exam scores. For instance, some schools might just have lower or higher exam scores, and they can have different relationships of parental income on exam scores. Just like before, we can set all of our other variables here. We can give the data to the model. We can say the family or the likelihood that we're going to use. In this case, we're just fitting a regular linear regression. So we're going to use a Gaussian or normal distribution as our likelihood. We're going to set it to give it our list of priors, and then we're going to set a random seed, specify the number of Markov chains to be 4, the number of cores our computer is going to use to do this sampling to be 4, and iterations to be 2000. Like before, I'm going to go ahead and run this, and then I'm going to come back when it's done because it'll take a couple minutes to run. All right, our model has finally finished running, so let's look at a summary. All right, so as normal, we get our regression model summary. We can see our best guesses or our estimates for all of the different parameters, as well as uncertainty around that. We can also check convergence, which, oh, interesting. Our R-hat is very close to 1. It's a little concerning, but nothing that I would completely throw the results out for. But our effective sample size is very small. By rule of thumb, we want this to be around 100 samples per chain, and this is definitely below that. Now, this doesn't inherently mean that the estimates you have are biased, but it does mean that your sampling is really inefficient, which might mean that you need to increase the number of iterations that you're running so that you get enough information to actually estimate your posteriors, or it could indicate that there's something wrong with how you've set up your model. In fact, this warning here, which says there were 240 divergent transitions, also indicates to us that there might be something going on with our sampling that we should investigate further. For now, we're going to move on, but in real life, what you would want to do is figure out, are there differences I could put in the way that I specify my model, for instance, with my priors, that might improve the number of divergent transitions and the efficiency of my sampling? Or if you didn't see a ton of divergent transitions and the only red flag was that you'd had a really low effective sample size, you might want to go back and have more iterations so that you give your chains longer to get more samples so that you can still get a good read on what your posterior is. Just like before, I probably want to also look at trace plots. Here, we have a lot of parameters, so it's a bit harder to read our trace plots, but you can see that while most look like fuzzy caterpillars, we are seeing some weird behavior pretty early in at least one of our chains, which may be something that we saw in the lack of effective sample size and the R-hat that was a little bit above 1. Now notice, the reason we have so many parameters is because we're using random effects. So not only do we have to fit an overall effect for the intercept and for the effective parental income, but we also have to fit it individually for every single school in our data, which is why we have so many parameters to sample. Next, like before, we might want to do a posterior predictive check. This actually looks pretty good, indicating that the model fit is not a huge red flag. Of course, we would want to go back and figure out why we have so many divergent transitions and why our effective sample size is so low. But at least when it comes to sampling from the posterior, there's not a huge amount of red flags showing that there's something very clearly wrong with our posterior distributions. And last but not least, what is an analysis without the ability to report and communicate the results to others? So I'm also going to use MCMC areas to look at the overall effect of parental income. It looks like in our particular sample, there's actually a negative effect of parental income. The more income that your parent makes, the slightly lower that your exam scores will be. Most of the density of the posterior distribution is to the left of 0, meaning that we're fairly confident that this effect is negative. All right, I hope you take the time to go over the code for these examples a little bit more deeply to try and familiarize yourself with using the BRMS package for Bayesian regression. But for now, that's all I have for you. I will see you next time.